So my cunning plan is, as I said, we've looked at F equals ma and W equals mg, and I want to look at different formulas that require the same type of math skill and the different aspects of physics that relate to. F equals ma is general, force equals mass times acceleration. W equals mg is a very special type of it that's solely to do with weight, which is a force, times mass, which is mass, times little g, which is acceleration due to gravity. Okay, so we did that last session. So this session, I want to have a look at momentum. Okay, now momentum is really cool. And like a lot of things, I've got a lot of fond memories about momentum. And I want to talk about it. I want to describe something. I wish I could find it, but I can't. And I'm going to start off with this thing here. All right. Now, it is, I can make it bold. Can I make it bold? Font style, make it bold. Yeah. I like it. Can I change its color? Let's make it kind of this red color. Magenta. All right. So I wanted to talk about the conservation of momentum. And I remember teaching this, and YouTube couldn't have been only like a year, maybe a few months old or a year old. And there's a really interesting video. Yeah, I'm showing my age, I know. So there was this young man, that's his nose, and he was stood there, and like a bit of a silly person, he was holding a shotgun or some kind of gun, and he pulled the trigger. Right? So when he pulled the trigger, the bullet shot forward, the gun shot backwards and broke his nose. Right? And we can explain this. There's also some really cool videos where you've got a pier in the water like this. Here's the banking, the river's flowing up and down here. There's a boat there. Someone steps out of the boat, and the boat moves backwards and they fall in. All right. This is everything to do with momentum. And I'm going to use this example here to explain to you what momentum is, why it's conserved, and how it's really cool as well. You get some really cool things going on. So first of all, the formula for momentum is pretty straightforward. Momentum, you got P. We can't use M for momentum because we use M for mass. And P's, I think, Greek, Latin, to mean Peter, to move forward. So momentum has a symbol P. So the first thing to be careful about is this funny P. Now the second thing about momentum, it is a really simple formula. Momentum is mass times velocity. Okay. Now velocity is not the same thing as speed. And I really want to talk about that as well. Velocity is what we call a vector quantity, which is a really complicated name, meaning that it's got direction. It has size, so we know how big it is, how big, and in which direction. And at GCSE and Key Stage 3, it's really simple. What it means is if I have a positive value, then I'm moving to the right of my exam paper. If I've got a negative value, then I'm moving to the left of my paper. So if I tell you the velocity is 10 meters per second, it means my velocity is on the right of my paper. I'm going in this direction. If it was minus 10 meters per second, then velocity will be to my left. Now, if velocity is a vector quantity, then so is momentum. We know which direction. So that's the first thing. The first thing is look how easy the formula is. Momentum equals mass times velocity, but it has direction. All right. So sticking with this silly boy who broke his nose, we're going to talk about the conservation of momentum. And I'm actually going to take that. I'm going to, right, come here, copy that. And I'm going to put it here. And we're going to start with conservation of momentum. And it's a really complicated sounding thing, but all it means is whatever my momentum was at the start, whatever it was at the start, it must be the same at the end. Okay. The thing you're also going to notice, and this is a side note, you will watch me draw the problem out. And one of the biggest issues I have with students is they don't bother. They try to do it in the head. Draw your problem out. And this is a branch of physics that we call mechanics. You need to draw your problem out. It really helps. All right. So when we look at this dude, right, let's take an image of this dude with a gun in his hand. All right. I should be able to select it all. Let me see if I can select him. Wait, almost. So there we go. So when you look at this dude here, all right. Now, before he shot the gun, nothing was moving. So the momentum at the start was 0. Conservation momentum says if it starts at 0, it must be 0. It cannot change. It has to be 0. All right. Okay, yeah, fine. How does that relate to this? So I'm going to make some numbers up. So at the start, the bullet is in this chamber here. All right. Oh, I pressed the wrong button. The bullet is here. And we're going to pretend. The bullet has a mass. So let's write these things down. The bullet has a mass of 0.1 kilograms. The gun has a mass of 10 kilograms. All right. So what happens here? What's going on? Before he pulls the trigger, the bullet is not moving. Its velocity is 0. So at the start, momentum at the start is 0 because velocity of everything is 0. And I don't care what the mass is. Anything times 0 is 0. So the velocity is 0. The momentum is 0. So what he goes and does is shoot the bullet. And let's say, for argument's sake, once he shot the bullet has a velocity of 1,000 meters per second. Okay. So the bullet is now moving. He's pulled the trigger. So what is the momentum of the bullet? All right, let's just move that across there. So the momentum of the bullet is momentum equals mass times velocity. Let's just zoom in. The mass is momentum equals 0.1 kilograms times the velocity, which is 1,000 meters per second. So the momentum, P, of the bullet is 100 kilograms meters per second. Okay, we'll have a look at why it's that unit in a moment. All right, but hold on, now we've got a problem. We've got a problem because we said momentum must always be conserved. All right, it has to be 0, but it's not. It's 100 kilograms per meters per second. Well, if that's the momentum of the bullet, once we fired it, then the momentum of the rifle must be the opposite, minus 100 kilograms meters per second. It has to be, because if it's not, they're not going to add up to 0. Right now, if I've got 100 kilograms meters per second, it doesn't add to 0. So the rifle must have the momentum in the opposite direction. So then we can ask a question. Dude, well, how fast was the rifle moving when it broke the silly person's nose? All right, so how fast was it moving? Well, we know if the bullet's got a momentum of 100 kilograms per meters per second, then the rifle must have a momentum of minus 100 kilograms per second. So we can write this out and say, right, the momentum of the rifle is minus 100 equal to the mass times velocity. Well, we know what the mass is. We'll put it up there. The mass of the gun is 10 kilograms. So, ooh, that's interesting. So I can turn around and go, aha, I know the momentum is minus 100. The mass is 10 times velocity. Well, I just want the velocity. So what I can do here is divide both sides by 10, or however you've been taught maths. So the velocity is minus 10 meters per second. Now remember what I said, minus means it's moving to the left. There's his nose. It's to the left of the rifle. The rifle will go bee and bang and break him his nose, and we know it's going to be moving at 10 meters to the second to the left. That, ladies and gentlemen, is momentum. And just over 10 minutes.